Let's see. I want to do a poll first. I'm into measurements. I'm going to measure the audience here because I don't think Susan did this morning. How many people here are actually from ISPs, providers? Wow, okay. So that's less than a full. Or actually, if you think you're from a provider, raise your hand too. Because I guess the definition's gotten a little looser this year. You don't need customers or anything. Okay, or at least not paying customers. How many people of those that raise their hands have looked at data on their network or someone else's network in the last week? And I mean like bytes or bits or TCP headers or something besides show IP, BGP on a router. Okay, now I know the 10 people in the audience that I'm actually giving this talk for. Great. The rest of you can take a nap. So this talk is about internet myths, and I don't mean what you find if you Google for internet myths, which is what I did before I wrote this talk because I wanted to get out of writing the talk too. When you Google for internet myths, you get, don't do it now, you just clog up the net. I'll just tell you what you get. Actually, if you do it by now, you might get my talk. You get lots of segments about internet marketing and sociology, and you don't need to read these. I'll read off the most interesting ones. It's cheap to do business on the web. This stuff really worked in the 90s, apparently. Advertising is flocking to the web in record numbers and will be its savior. You can give away the merchandise as long as you generate enough eyeballs, because one day you will be able to monetize those eyeballs. If you have a clever URL, they will come. People will never pay for content over the web. I can't even read these. Traditional advertising brings eyeballs and will generate much traffic. People like to shop on the web. That's my favorite. People like to shop on the web. People like to buy on the web because they don't like to shop. Let's see. It costs nothing to get a site up and running. The web is a reliable commercial activity, and just wait, profitability is right around the corner. Yes. Oh, yeah. Ads are on the web at that URL. Is it not linked? Okay. Everyone got them? Yeah, because I'm going to go through these fast, and most of you guys aren't paying attention anyway, so you want to get the slides on the web. Okay, these are not myths. These are fantasies, and let me just distinguish between fantasies and myths. Fantasies, no one actually believes. That's what this list up here is. People want them to be true, and actually people make money by convincing others that they're true, in particular marketing people and advertising. But myths are things that people actually believe that are wrong. Who believes fantasies? Marketing, advertising, lawyers, consultants, I guess, maybe addicted drug users. Who gets hurt when people believe fantasies? Well, I don't think anyone. I mean, fantasies fine, consenting adults, marketing, advertising people, they're expendable. I'm sorry if they're marketing and advertising people in the audience. I'm not sorry for what I said, I'm just sorry if you're in the audience. Okay. Myths, who believes them? Well, researchers, vendors, policymakers, journalists, secretaries of defense. Really? Potentially marketing, advertising, lawyers. Let's not worry about them and these addictive drug users as well, but they can believe it more. Who gets hurt? Well, people really get hurt. Things really get hurt with myths, when myths are believed, not like fantasies, okay? Packets get dropped, engineers get paid, protocol developers build things like ATM and MPLS. Graduate students spend 10 years of their life doing completely useless, not that I speak from experience, decades of youth are lost, and the economy is plunged into global recession because people aren't looking at the data. So I get a little preachy on this one. So this talk, and I'm going to mix in, as you can tell, some sociology and random nonlinear leaps of logic. This talk is about internet myths relevant to engineering. That is, it's about internet data. I categorize them into these 4 different categories. I've given this talk, I give talks before on internet measurement and data. And I divide things up into 4 categories because it gives this pretense that I have any organization in my research. And the categories are, and I'll describe them a little bit, and then I'll go through this list of myths, walk you through them in the talk, and then I'll put the slide up at the end, and you can get all this on the web. So I'm not going to go through these things now, but the upshot is that there's crap all over, all kinds of measurements that people believe that's just wrong. And this is just stuff I came up with in a week. I could come up with another same amount of these in another week at Wrestling. Why so many? No real measurement. Okay. Okay, so I can skip these next 3 slides and you can page through them because everyone at NANOG knows and I've given this kind of crap for 10 years. And I could write a book, I guess, but it would be really short because it would just be these 3 slides. Why the internet isn't measured. Internet's a pain in the ass to measure. Everything's moving too fast. There's no equilibrium. All the measurement tools suck, basically. They don't help ISPs solve what ISPs need to solve. ISPs need to invest a lot of effort in deployment and cost and colo space and stuff. So losing battle, even though everybody admits that more data would be better, researchers would benefit, vendors would benefit. People come after me all the time. ISPs, unfortunately, are the ones that would bear the cost of doing this. So until we can sort of rearrange the cost structure and have somebody else, other people share the cost, like sort of transfer the cost before that they're actually incurred, which if any industry can do it, it's the internet, I guess, and the drug industry or something. But two ways to do it besides that is build tools that are actually going to make an ISP profitable. That's kind of reaching right now. Make them less unprofitable. And then you could do it, just make it illegal not to measure or something. So you got regulatory and technically useful or economically useful tools. So what happened in the last 5 or 6 years instead of measuring the internet? And hey, I was busy, but a lot of people weren't busy looking at data. So Andrew Adlisko, this completely insane, even crazier than I am, there's a benchmark, wrote this paper in November of 2000 called Myths of Internet Growth. And I took a lot of this idea for this talk from him. And he actually just last week wrote another complete slam of another, thank God he did this because now I don't have to, of this thing Larry Roberts did, Casting Networks. You guys might have heard of this. It's this PowerPoint. So, oh my God, don't even get me started. Well, it's too late. He wrote this slide set about this growth of internet traffic and just explosive growth predictions, and that's why everybody has to go buy his boxes, I reckon. I don't know. But anyway, back to November 2000. Andrew wrote this paper, and he gathered all the data that he could realistically get, and he also uncovered a lot of the beliefs that were going on before he wrote this paper, right? So back in 1995, people were starting to talk about this explosive growth in the internet, exponential traffic doubling every 90 days, and you actually hear people that you really respect and you trust this number. The reality is that, I mean, the last time real stats on the backbone were available was NSFNet, right? Somebody, he was this tutorial on Sunday was talking about NSFNet stats, which lasted until like 1995 or middle of 1985. I think they stopped doing the stats, and you can still get all those stats at some FTP directory. And so there was like 3 months at the end of the NSFNet backbone, right when the web was coming out, when traffic doubled, like for 1 3-month period, and that was the last number that people would refer to for like a year or 18 months, even though traffic never grew that fast again on any, well, with any numbers or evidence that anybody has. It doesn't stop the financial markets from continuing to use that number and generate all this irrational capital markets. So if you do the math, though, over 6 years, this 90-day doubling would mean a factor of, what, 16 million or something. So in reality, there's been no real data since 1995 about the global quote backbone, whatever that would mean. The math just doesn't really work out. You can see these bullets here. Basically, I did this math. Assume that you have half a billion users of T1 using it around the clock. That's what a factor of 16 million would be. Because we don't even have that. I mean, everyone's really still at modems. A huge, vast majority of us are at 28K in less than an hour a day. When I mean us, I mean my mom. And at less than an hour a day. Anyway, upshot. It took 5 years for this true traffic growth data to manifest itself, basically in the form of how much Cisco and Juniper routers ISPs were buying, or some other economic data that you have to legally turn into the SEC. And that's actually when we finally realized how much traffic wasn't growing on the internet, because we don't have access to real data on the internet. So from my perspective, that's actually fairly pathetic, embarrassingly pathetic willingness to ignore or invent data. No data. Well, okay, trade-offs. Let's talk about trade-offs. So there's certainly cost, and I argue the tech stack bubble was largely affected by our lack of actually looking at what was going on. Retarded some technical developments. You end up getting a tremendous amount of emphasis on certain technologies to handle the growth that didn't really exist. Geez, what a waste of time. But it did have some benefits. You end up with this unparalleled platform for innovation. Open standards, rapid development of new services, and huge empty pipes were a key factor in supporting the quote revolution. If the pipes weren't empty, you wouldn't have had Napster. It wouldn't have really worked, right? So it did allow some sort of next generation of applications for people being gutsy. And we learned some lessons like we need to amortize cost of pipes differently. Well, we're still trying to work that out in the industry. Come to terms with a much looser definition of capacity planning, and basically simplify the architecture. That was the biggest thing we learned, the fact that, well, if we're not going to look at the data, we better have a really simple plan. Now we're living on borrowed time. So this is my main argument that, okay, everything's, sky's not falling, but it's cracking. And if we want to really get to this third wave, and that's not my terminology, people talk about waves of applications, first wave, second wave, third wave. The first wave is, email, telnet, 1980, whatever. Second wave is essentially the web, client-server model, formatting languages, distribution of content. Third wave is more collaborative peer-to-peer stuff we're seeing this year, the last couple of years, I guess, Napster, Kazaa, gaming, video stuff. So and these are also called NGI by, who calls it that? Federal agencies call it that. It basically means give academic research. NGI, I think it's like give academic researchers money to pay providers to do stuff that can't be done anyway or something. That's what I see NGI money going to. And the growth of these newer applications, though, is going to be self-limiting, obviously, by user frustration with performance, if nothing else, unless we have either a better grip on measurement or infinite pipes everywhere. So I don't know which one of those is more likely. Okay, where are we right now? Sorry. Oh, by the way, Susan said I was allowed to let you guys interrupt with questions. If you have questions. Okay, so now we're going to the actual talk. All that was leading up interest. Don't go to sleep from now on. If you go to sleep, don't wake up, because if you wake up after this point, you're going to feel like a bad acid trip or something. 4 categories. CADA works in all these areas, basically building measurement tools, analysis techniques, identifying priorities, obstacles for the people that are working in the area, yada yada. So here we go. Workload is what's on the net, what's in the packet. Is it mail? Is it Napster? Is it web? Where is it going from and to? Is it intercontinental? Is it what's the packet size distribution? Things like that. Things you have to look inside the packet header to get. That's workload. Or you can count SNMP stats as workload too. Amount of volume of traffic. Topology. Mapping, what's the internet look like? Variety of levels there. You could talk about layer 3, layer 2, layer 4, hierarchy layers or logical layers like cache hierarchies or M-bone. 3 is performance evaluation. This tends to be end-to-end, things like latency, loss, throughput. Routing. Not to be confused with topology, even though it's impossible not to. I'll explain the difference when I get there. Okay, so let's start with workload. So I'll sort of tell you when I'm done with each category to keep you guys caught up. Here, first, IP fragmentation. Now, I don't know how many people in this room are sort of familiar with this myth, but there's a myth, and I see it quoted in SIGCOMM papers, that you can assume some certain technology will work because of the use of fields that are used in fragmentation, but you can reuse those because there's no real fragmentation on the internet, or less than 0.005%. Not true. So the myth there is that there's no fragmented traffic. It's true that a small percentage of traffic is fragmented. The number is actually growing, and some protocols have more fragmented traffic than unfragmented. It does not exist only in LAN, the way a lot of people think about. We have monitored aggregated exchange points and backbone links that all have fragmented traffic. TCP traffic is never fragmented. Wrong. TCP is definitely fragmented much less than others, but because of path and queue, but certainly we see it, and actually quite a bit of fragmented tunneled traffic is TCP due to a lot of people that build or make 1,500 byte packets that then get tunneled, add a header, then it gets fragmented, 1,540 bytes. Lovely stuff going on. NFS causes almost all fragmented traffic. Wrong. Fragmented traffic happens in a lot of protocols. Okay, myth 1. There's a second myth that actually is a bit of a sky is falling myth propagated by one of my favorite people on the internet, actually. But he's going to argue with the way I present the slide. The myth is essentially the number of, there's a correlation between the number of hosts on the network and the amount of bandwidth used. It's an n-squared law. Is the more hosts you have, increased hosts by n, increased bandwidth by n squared. Because, you might imagine in a peer-to-peer model, there's some sense to that. We don't actually see that in any of the data that we've looked at, that the correlation between host pairs and bandwidth is much lower. Growth is much slower than linear even. It's definitely not a square. And this is using basically packet traces, whole packet traces from which you can get utilization stats and others from 20 different academic sites, which is where the newer traffic is presumably coming from. So it's where to look at future trends. Over 4 years. So the growth spans many orders of magnitude, but you never see this host pair, this square law that some people are worried about. Same phenomenon here, but using too much math, so I'm going to skip it, but you can see that on the web. Oh, here's a great one. I love this one. It also introduces, Andre's going to give a talk tomorrow, but this is one of my favorite Andre laws. Andre's doing this one. Freud's law. Private addresses do not appear in the core. Now, Evie just did a talk about how you see private addresses in the, not only people asking the root service for information about RFC 1918 addresses, but actually the source of the packet is also an RFC 1918 address sometimes. So this is a list of in our CADA macroscopic topology mapping project, how much junk we see in IP addresses and trace arts that just shouldn't be there. So this includes, you know, multicast addresses and 10 dot addresses and things that just absolutely shouldn't belong. So Freud's law is what shouldn't be seen in the internet is seen about 1% of the time. He's actually studied a lot of different things where this law applies. Interesting. Another workload myth, mice versus elephants. You guys might have heard this. This also gets tossed around the research community quite a bit. 1090 rule or 2080, depending on who you are, who you're talking to. But there's a prevailing belief that, you know, 10% of the flows are constituting 90% of the traffic. It's a some measure of traffic and some measure of flows. In any event, all the data we look at, it's all over the map. It's some, you know, it really depends what kind of applications you have on there. We've never seen a 1090 rule true for packets in any of the traces that we've studied. And it changes not only by site, but also by time of day, again, based on my applications. So, no fast rule about internet traffic there. Oh, I hate this one. This is about my campus. So, unencrypted passwords are mostly gone off the internet, right? Okay, so this, unfortunately, now, I warned UCSD that I was giving this talk at NANOG. This is my campus. This is UCSD's umbilical cord to the network. That's not web traffic in light blue. That's the number of unencrypted passwords seen on the link to campus, which means it's not staying on campus. It's people dialing in from home and sending their POP password in a class clear text, even though APOP is fully supported all over campus. So, I mean, this isn't going to be a surprise to you guys, but the existence of encryption doesn't mean it's going to get used. I like this one. Actually, U.S. government, okay, the myth, U.S. government can stop file sharing. This is actually in the fantasy category, I have to admit. I got this one. Okay, so red, can everyone see the graph? Red is Napster. And this is just, I'm just looking at emerging applications here, so there's eight applications listed in the legend are things like Nutella, Napster, Fast Track, Real Audio, Quake. Well, AOL doesn't really count as emerging, but I have AOL, it's in the noise in here. iMesh kind of stuff, Scour. It's a lot of peer-to-peer and sharing of large or whatever kind of files. Never porn, I'm sure. So the red is Napster, and the blue is Nutella, and the orange is Kazaa. And that little death of red thing was the day that they kind of shut down, or the time in which they were putting an immense amount of pressure on Napster to shut down. This is back in August of last year, I forget. So you see Kazaa just sort of takes up the slack there. And that is measured in how? Okay. So next one, now we have a week of data. So this last one was a year or whatever, many months. It goes from December to December. So that's a year of data of 2001. Okay. So the myth here might be, you know, because since obviously U.S. government is stopping file sharing, that's a fantasy. The myth might be that there's still not a killer app. We haven't seen the killer app yet, which I do hear a lot of people say. I think they're still waiting for multicast to take off. I don't know what's going on there, but there's definitely a killer app, and I'll walk you through it here. Here we go. Eric Schmidt, he gave this great keynote last year at a DNS workshop in July. He said, how do you know when something is a killer app? When every university, he's the CEO of Google right now, I think. He's a great guy. When every university tries to stop it and can't, that's how you know it's a killer app. That it takes a federal judge to threaten to put you in jail if you don't stop. That's killer. Okay, this is bits again. What do we got here? And just in case you thought it was big packets, in which case the packet count would be smaller, because the bit count would be high. There's a lot of packets here, too. This is measured in packets. It's an interesting similarity. Actually, so I'm going to throw sociology in here now. I'm old enough. This is history. I remember when Gopher was really big until the web just crushed it in its palm. And part of the reason was, not that anyone would know this from looking at data, because no one did, But if you knew the politics behind it, Gopher, the University of Minnesota, was clenching down on this and wanting a patent for it and wanting to control and license all this junk exclusively. Forget that. So CERN was all about just get HTTP out, make sure it's public. Gopher just disappeared off the face of the planet. So here you have a similar thing happening with Napster, where instead of controlling the intellectual property, you control the port number. Get rid of that because I doesn't need the port number. So I thought that was pretty interesting. Okay, next. Oh, in case you thought it was just a few punks sharing porn files across the internet, this is measured in flows. So I've now shown you bytes over a year, bytes over a week, packets, and flows. And admittedly, this is just the emerging applications. It's not, web isn't included. Web still dwarfs all this. Oh, I wouldn't say dwarfs anymore, but this is exactly what the web looked like. This rate of growth that you see, like back here, and then to that. It's exactly what the web looked like in '95. So no killer app? You got to be kidding. This is a killer app. That's not neat. Okay, we're done with the first category. Moving right along here. Second category. David and Colleen and a couple of professors at UCSD did a study last year on the prevalence of... Actually, David Moore gave a talk at NANOG here on this one. I think he gave a couple of talks, merged two talks in one. But the upshot is, okay, myth. DOS attacks typically affect only large commercial sites, last a pretty long time, and are at extremely high rates. So we saw in this 3-week period that we studied last year, over 12,000 attacks against over 5,000 targets in 3 weeks. We have this facility to sort of measure the background level of a certain kind of DOS attack, and I'm not going to explain the methodology, but it's in the paper, it's on the website. 20 to 60 attacks occurring at all times of this one kind of source spoofing attack. 80% of attacks are less than an hour. A few last for 3 weeks. 70% of attacks are less than 1,000 packets a second. A few are huge. 10 to 20% of attacks are essentially to what we presume are residential users, cable, DSL, dial-up, or small businesses. 3% of attacks target the infrastructure directly, routers or DNS servers. Here's a picture. I'm getting into pictures. This is, what is this? Week 1, 2, 3, 3 weeks. Category x-axis, what TLD was attacked, and y% of attacks. So it didn't change much over the 3 weeks, you can see, and the biggest one is what is it? Attack. Hold on. I can do this. Victims. Yes. Victims of attack. So you put a source port of this thing that it's going to get the response back, right? That's what these are. So biggest category of most things on the internet is unknown. So that's what this is on the left. And then net, com. A little bit of disproportionate. After com, number 2 is net, number 3 is com. Romania, Brazil, go team, and then org in edu in Canada, and then it goes on. And actually, it's essentially very similar ratio to the number of machines that we believe the country has. So it's not like disproportionate. It's about as many as you'd expect, except for Romania and Brazil. I don't know what's going on. Worm spread, code red. Okay, so here's more myths. People, especially in CNN, this was kind of freaking us out. Except in San Diego when David actually got interviewed by local news, that CNN was clearly saying at the very beginning of Code Red that you did not have to worry about this as a home user, scaring the bejesus out of us, because it was a huge number of home users were affected and reinfected every time they rebooted their system, thinking they were cleaning off their disease or whatever. So left big huge spike there is home.com, that's typically residential or small businesses, and Roadrunner, another cable modem, Dial-In, next, Paxel.net, next, and then you AOL, HiNet. But huge amount of home users and business users, so they're a very critical, important aspect of global internet health, even though there are no sysadmins at my mom's house. Myths. Okay, so this depends who you are, whether you believe this or not, but a lot of people have just given up on the idea of any correlation between geography and latency. So we've done a lot of studies with our topology project because we do a lightweight trace route to millions of destinations, cover the V4 space all the time. And a very slow rate, but all the time. So we end up gathering a ton of delay data to the end host, and we plot this. X-axis is distance, geographic distance. Y is round trip time, and the color is sort of the density of plots. So if you could imagine 3D, and the color is sort of the third dimension, there's a ton more green than red or black. And so there's actually a clear kind of correlation between the speed of light, kind of what you're seeing there, and then that white junk in the middle is the ocean, one of the oceans, depending, because it's raw distance, it's not longitude. All right, so there is definitely some correlation between geography and distance. And it's not necessarily, and we're still doing some studies on a variety of distance metrics that you want to use for those most predicted power, AS hop count, IP hop count. Okay, so this is going to contradict Evie a little bit. Performance myth, the root DNS system performs well. So Neville is one of our researchers actually that's done, what he does is pretty interesting, and maybe we're going to give a NANOG talk at some point. Passive analysis of DNS queries and responses sent from certain client sites. So he'll set this monitor up at a campus, and if you're interested, you should definitely send me an email, because we'd like to get a big web page of these things in order to correlate performance to all of the DNS server, the root and GTLD servers from a variety of sites. So what he does is, this is called a strip chart, and the absolute values don't matter, because the idea is that he's plotting 13 delay time series along here, and it's the 13 root servers. So the fact that it's so jaggedy is a bad thing. And if the spikes were correlated vertically, if they're sort of lined up vertically, then you could kind of impute it to local connectivity problems. But the fact that they're spread all over the place, and there are quite a few that are consistently really poorly performing, that sort of are masked, as Evie alluded to, masked by the well-performing, better-performing DNS service, root service, since you only need to really use one. Now, Evie did this part of the talk, so I can skip this entirely, but let's see, what do I have here? Bogus A query she did, query asking for the IP address of the host name. 14% of that, she did that, 20%. I have to tell you just one thing she didn't mention. And remember Evie's very good, bless her heart, even with Microsoft, which takes a huge amount of effort, at trying to find the right person and get a bug fixed. So, this is going to embarrass me. She sends the guy mail, and Microsoft sends back, it's better if we have an RFC number that to point to the bug. And maybe this is true in other vendors too, because that means we can get it fixed faster if you can put an RFC number in the DTS or whatever, for the trouble takes the So she sends Vic's mail. She says, I looked in the RFC and I can't find where it says not to ask for the IP address or an IP address. This is Vic in his eminently wordy fashion. He responds back, he goes, what the hell? That's like putting in the RFC, don't forget to breathe. So I'm not putting that in the RFC yet. So Evie did not have an RFC number to send to this Microsoft person, and he had to go fight for himself within the company. Single router key tracking net, she did this too, February. Microsoft put all its DNS service behind this, all its authoritative service behind this one router, and now all you need to do is mistype a semicolon, and in fact someone did, and she gave us a sob story about that. But yeah, one router can certainly have a huge effect on the global infrastructure. Topologies, these are a little bit more esoteric, so I'll go through these fast. But just to prove to you that there's myths everywhere, I'll give you 3 topology myths. Big thing, if you're geeky enough, or if you have geeky enough friends that read these research or write these research papers on topology and power laws, you'll see power laws thrown out all over the place. So like out-degree distribution of ASs or of IP addresses follows a power law, yada, yada, yada. I guess if you're lucky, you've never even heard this, but I have to face it all the time because I see all these papers that talk about power laws. So what we found when we look at the finest granularity data that we can get, which is the skitter data that's based on a trace route, is that the distribution, the out-degree distribution, I'm just going to assume everybody knows what that is, but it's a number of outgoing links from a given node, where a node can be IP address or AS or whatever your graph is. And here it's IP address. The node is an IP address. And the out-degree distribution is the black vertical straight line down is a power law fit, and the green line that coincides with the red line, which is the data, is a Weibull fit. So using more finer grained data than these other papers that have been published that talk so much about power laws and different aspects of internet topology, shows it's clearly not a power law. It's much more of a much closer to a Weibull distribution. This is another one of Andre's topology discoveries. Another topology that's routing table data reflects VGP table data, in particular reflects topology, even AS topology that's actually taken. So because CADA has access to these huge IP-based topology sets, what we can do is take a routing table, which is AS granularity only, and take an IP graph, which is IP addresses, and collapse the IP graph into forward ASs just by mapping an IP address to an AS. Guess how we do that? We use a routing table. It's not as circular as it seems. So you end up with these two AS graphs, one gathered from a BGP cable and one gathered from forward probing and then collapsing down. And you end up with a ton more connectivity information from the IP graph that you just don't see in even the 50 or 60 routing tables that you can get from the best available routing table that we can get right now. And this graph just says x-axis and y-axis are the degrees of these two different types of data. And if it were in the center, if all that junk was on the diagonal line, then it would be approximately congruent kind of data, equivalent types of data. Because things are leaning so much more below the diagonal, it means it's capturing a lot more connectivity information using the forward probe data. That's all that means. One last topology myth, because I can tell I'm losing everyone because I'm getting bored of myself. Another libel thing. Okay, so everyone also thought this is a parallel. There's tons of stuff in internet that people think is parallel that really turns out to be libel, according to Andre's work over the last 2 years. And here's one: number of IP addresses that are observed within a single AS. Again, you see the parallel line. Data fits the libel much better. Okay, now we're done with the parallel stuff. Oh, I have a question. Okay.
Casey, do you know if you're picking up any VPN sources in your end-to-end IP queries?
Say that again?
Are you picking up virtual private networks? Are you picking up IP addresses behind NAT boxes?
Well, it's hard to know, right?
Yeah, the question is in your end-to-end studies, did you actually target users which are behind that?
No.
So you're pretty much targeting. So this is the part that we can see in the global internet, not the.
The internet's much bigger than we think.
Is the internet an iceberg?
Well, we don't see them on purpose. No, the answer is no. That's the right one. So this is sort of you're the Weibel. We got Weibel all over the place. Next, we go into topology. Last thing. Now this. What am I on time, Susan? Okay. I could make new stuff up. Routing, last category. And Andre actually is going to give a talk on this tomorrow, much more detail than I am, with a bunch of really cool discoveries. So definitely, and very misexploiting discoveries, but I don't want to steal all of his thunder, so come tomorrow, whenever, 10 a.m. or something. But here's one interesting routing myth, is that, I don't know how many of you guys really believe this anymore. You're operators, so you shouldn't believe this, except that you probably never look at data, so you probably do. Intra-country traffic stays in the country. So, like, for example, traffic from Japan to Japan. So we have this monitoring point at the commercial backbone in San Jose, and what we end up seeing there is a ton of, and it's a link that ends up going to Asia. It has a lot of routes to Asia. But we see a lot of traffic that we can identify the source and destination IP addresses as both being in certain countries. And this 3D graph is just the traffic that's from Asia, from Asian countries to other Asian countries through this point in this exchange point type area in San Jose. And so the diagonal, obviously you see a lot of traffic coming through the U.S. because it's a hub and it's cheaper to get up, or not cheaper, but it's imperative to get a pipe to the U.S. So additionally buy a pipe to other countries in your area, since the default to the U.S. will get you everywhere, U.S. and everything. And that's actually what you see. I'm not saying this doesn't make economic sense, but the diagonal is actually countries to itself, traffic from countries to itself through this point. Again, I've seen this kind of stuff for years. It doesn't really surprise me anymore, but a lot of people think that traffic stays in the country if it starts in that country and ends in that country. All right, and then, here's another great one. I've heard many people say, the internet's getting more meshier, the AS path length is decreasing because there's so many more ISPs, even back when there were a lot of ISPs and you did have paying customers. But we've watched over the last few years, and this histogram, it's so cool to see a graph like this, by the way, because you never see bell curves in any internet data. This is the closest you get to normal data, and it's an AS path length distribution over, how many years is on this? 1999, 2000, 2001, 3 years. Over the course of 3 years, 6 peers, 6 different routing tables, and it just doesn't look very much. If anything, if anything, it's increasing. It's not. It decreases for some and increases for others. And here's the linear over time, just using the average, which, if anything, is increasing. So AS path length is not decreasing. Median is still 4. Tell all your friends. Okay. And then here's a list of stuff that you're not going to be able to read here, which is fine, because this is a very short summary of Andre's talk, which I give this slide when I'm at a place where Andre's not going to talk. But you guys are lucky, and Andre's going to talk. But the thing to come prepared for is that he's going to explain that the routing table growth and the routing table churn does not, in fact, come from where a lot of slide sets say that it's coming from. And it's certainly no longer exponential or explosive. Andre reminds me that every 1% is still exponential for some exponent, but I don't like the way that's that. So, peering richness is growing. Well, actually, in our analysis, we find that things have pretty much stayed the same. Again, you have a lot of changes within individual ASs in both directions, but there's no overall trend that you could say is statistically significant. Another myth, small ISPs and multi-homing cause the growth and or the churn. Since 1998, for example, the share of /24s has stayed pretty constant. This is all using route views data, which has increased the number of peers over the last 3 years. Number of non-transit multi-homed ASs grew a little bit, but their share of global routes remained pretty stable. The upside of these things, I'm not going to read these all because Andre is going to give this talk much better, is people are making assumptions about what is causing the changes in the routing tables, and they're not verifying them with enough data. They might be looking at their own routing table or 1 or 2 routing tables, but they're not verifying with large enough data sets over long enough periods of time. Okay, now I just gave you this whole talk, and then we're done, pretty much. And we're going to show a video now, a 3-minute video. Yeah, we're definitely doing questions first because I'm so not answering questions after this video. But this is a list of all the things that I've gone through. You know, there's myths in every category of internet measurement, of thinking about internet data that you can imagine. And I've only given you a sample. Implication. We've shed doubt on many commonly seen internet myths, even with use of a number of data sets, and CADA actually has some number of data sets, not as many as we need, but we as a community have really quite low integrity in drawing any macroscopic inferences. Could make much better use of our collective intellectual resources. Well, this sounds really preachy, doesn't it? I should write a book. No, I'm not going to write it. Validate ideas against, if we could validate ideas against a larger variety of empirical data sets before investigating research and development, time and energy on ideas that attempt to affect the infrastructure. I think I just made a lot of enemies in here. All right, this is just proselytizing stuff. You can read it on the web. I'm going to start the video if we can get the lights down.
No, wait, I have a question.
Oh, that's right, Susan has a question. Nobody else has a question.
This came in from someone.
Oh, yeah,
He refers to page 22, which must be your 22nd slide.
Really hard. My what?
22nd slide, maybe? He says page 22.
Yeah.
There's a 10 to 20% of DOS attacks towards, quote, home machines, and 5% to infrastructure. Can you tell us what the other 75% of the attacks are targeted against?
These. I mean, just random.
And the answer is, say it so that...
it's targeted to, all across the internet in approximate proportion with, where the hosts are.
Uh-huh.
But it's the point of that slide, the point of that story was that unlike what the common media is saying, DOS attacks are not strictly a threat against commercial enterprises. It's not the case that mom and dad do not have to worry about DOS attacks to their or behind their modems. Or other questions? None. Great. Is it none? Maybe not none. Oh my God.
Is there anything that isn't a myth that's disproved by data?
I didn't even include them. I left off the ones like there are no invariants in the internet because Andre keeps coming up with new invariants, and I just didn't have time to write that talk. Are there? It depends. See, I don't believe any of this stuff, so it's not myth to me. I'd have to think about that one. I'm sure there's the routing table is growing. That's not a myth. That's what I think it's